got me thinking. I was at a diner the other day and saw this kid with a seriously long straw. It got me thinking, why don't we have super long straws, like meters and meters long? Wouldn't that be fun? Or is there actually something in the laws of nature stopping us?
That's a great question, and honestly, the answer is more about physics than design. When you drink from a straw, you're not technically sucking the drink up. What you're doing is reducing the pressure inside the straw. The pressure from the air outside, mainly nitrogen and oxygen, then pushes the liquid up the straw towards your mouth.
So my childhood dream of sipping soda from the next room is crushed by air pressure? How long could a straw really be before it just stops working?
About 10.3 meters, or around 34 feet, is the absolute limit, even if you had a perfect vacuum inside the straw and materials that didn't collapse. That's because atmospheric pressure can only push a column of liquid so high before the pressure from the liquid itself balances out the air pressure outside.
That makes so much sense now. The idea that air is actually pushing soda up the straw is kind of wild. But what exactly is pressure, really? How do these tiny molecules create a force we can feel?
Imagine a gazillion miniature ping pong balls bouncing off every surface around you. That's basically what gas molecules do. Each collision with the walls of a container, or even your skin, exerts a tiny force. Add up all those collisions, and you get pressure. At sea level, the collective force of all those molecules is what we call 1 atmosphere of pressure.
No wonder our bodies notice when the pressure changes, like when our ears pop on airplanes. It's those molecules colliding less frequently as we go higher, right?
Exactly. As you ascend, the air thins, so there are fewer molecules per cubic meter. That drop in pressure is why your eardrums feel the difference. It's also the reason why weather, balloons, and even breathing are all tied to pressure changes.
Now I'm picturing a room full of invisible, hyperactive ping pong balls. But why do gases act so differently from solids or liquids? Like, why are they so easy to compress? Or why do they fill any container?
It all comes down to the kinetic molecular theory. This model says that gas particles are in constant, straight-line motion and don't really interact with each other. No sticking together, no repelling, nothing. Since there's so much empty space between them, they're super compressible and can spread out to fill any container you put them in.
I never realized how much empty space there is in a gas. If you turned the liquid in a soda can into steam, would it really take up that much more room?
Absolutely, it's a jaw dropper. That 350 milliliters of liquid can turn into about 595 liters of steam under the right conditions. It's all that space between the gas molecules that makes the difference.
That reminds me, I've seen videos where divers get into trouble if they come up too quickly. What does that have to do with gas laws?
Great connection. That's all about Boyle's law, which says that if you decrease the pressure on a gas, its volume increases, as long as temperature stays the same. So, a scuba diver who breathes pressurized air at depth, let's say at 20 meters, with 3 atmospheres of pressure has lungs full of air at that pressure. If they shoot up to the surface too fast without exhaling, the pressure drops to 1 atmosphere and the air expands, potentially tripling in volume. That can be extremely dangerous.
So that's why divers have to ascend slowly and keep breathing out on the way up. The expanding air has to escape, or else, yikes!
Exactly. It's a life-saving application of Boyle's law. And the same principles explain why a balloon shrivels up if you put it in the freezer. Charles's law kicks in there, linking gas volume and temperature.
All these laws, Boyle's law, Charles's law, Avogadro's law, are starting to feel like one giant puzzle. Is there a way they all fit together?
Definitely. The ideal gas law ties them all up in a neat bow. PV equals nRT. It combines pressure, P, volume, V, amount of gas in moles N, temperature T in Kelvin, and a constant R. This single equation can describe almost any situation with a gas, as long as things don't get too extreme.
That equation has popped up in so many chemistry problems. And now, I know it's not just academic, it explains everything from how airplanes pressurize their cabins to how we measure air pollution.
Exactly. And speaking of air pollution, these principles also help us monitor and regulate the gases in our atmosphere. From reducing harmful emissions to keeping our city's air healthier, understanding gas laws has a real impact on our daily lives.
Something else I've wondered about is how breathing different gas mixtures affects people like astronauts, divers, or even just folks living at high altitude. How do partial pressures play into that?
Partial pressures are huge. Our bodies are tuned to breathe oxygen at a specific partial pressure. If the total pressure drops, like on a mountain, the oxygen partial pressure drops too, and that can cause altitude sickness. On the flip side, divers breathing too much oxygen at high pressures can suffer oxygen toxicity.
That's why deep-sea divers use special gas mixes, like heliox, right, to reduce risks from both oxygen and nitrogen.
Exactly. Helium replaces nitrogen to avoid nitrogen narcosis, and the oxygen fraction is carefully adjusted. It's all calculated using Dalton's law of partial pressures, ensuring each gas is at a safe level. Even managing cabin air in planes comes down to these same ideas.
The more we talk, the clearer it gets. These gas laws aren't just for lab experiments. They're everywhere, from the soda we drink and the air we breathe to public policy on pollution.
Absolutely. And it's inspiring to see how understanding something as simple as how molecules move and collide can lead to cleaner air, safer diving, or even safer flights. Chemistry really shapes our lives, often in ways we don't even notice day to day.
I guess next time I use a straw or board a plane, I'll be thinking about molecules, pressure, and Charles's law. There's a whole universe in something as simple as a breath.
Who knew? That's the beauty of science, turning everyday moments into a window on how the world truly works.
Alright, that was chapter 11. I also sent you a text of like a rundown of a summary of that, so hopefully something of that made sense. But it's really just the gas laws, and a lot of them are interchangeable. Just make sure your units are correct, and you should be alright.